Welcome to Session 10, Linear Equations and Systems. This lesson develops mathematical reasoning that stays reliable when a problem looks unfamiliar. You will learn to preserve equality through each operation, to choose elimination or substitution, and to verify a system in both equations. These are connected habits, not isolated tricks. Keep a pencil ready. We will build a mental model, use a repeatable method, solve a demanding example, diagnose an error, and finish with an independent checkpoint. Start with this principle. A system solution must satisfy two relationships at once. Use this visual structure. Translate is greater than eliminate or substitute, is greater than back minus solve, is greater than check both. Read every symbol and label before calculating. The first goal is to preserve equality through each operation. Connect it to the second goal. Choose elimination or substitution. Correct calculation begins with correct interpretation. When the surface details change, search for the same relationship underneath. Transfer means choosing the structure from evidence rather than waiting for a familiar-looking example. Step 1. Define variables and translate relationships. State the target and preserve its units or conditions. Step 2. Choose the variable that is easiest to remove. Use a separate line so signs, factors, and labels remain visible. Step 3. Solve and back minus substitute. Keep the reasoning efficient, but never skip an operation that could hide an error. Step 4. Check the ordered pair in both originals. Verification is part of the solution because it tests the answer from another direction. Signal 1 is, a variable is isolated. Respond by remembering. Use substitution. Name the response before calculating. Signal 2 is coefficients are opposites. In that case, use elimination. The form tells you which tool fits. Signal 3 is same slope, different intercept. Remember, recognize no solution. This separates plausible work from valid reasoning. If you cannot name the signal, pause and classify. A deliberate choice of method is usually faster than repairing a rushed setup. Here is the challenge. Solve 0.3x plus 1.2 equals 3.6. Restate what is requested before touching the choices. The first move is define variables and translate relationships. Apply it directly to the quantities and conditions in this problem. Now use the core reasoning. Subtract 1.2 to get 2.4, then divide by 0.3. Keep each equality, comparison, or unit conversion visible. Pause for a midpoint audit. Check copied values, signs, units, restrictions, and whether the current result is the requested quantity or only an intermediate value. Continue by applying this control. Solve and back minus substitute. The explanation supports one option without relying on its position. The mathematical conclusion is x equals 8. State it with any required units, interval notation, or restrictions. The final answer is x equals 8. Compare it with the exact target and reject any choice that represents a common intermediate step. Verify from another direction. Substitute the ordered pair into both original equations. The check should use evidence independent of the original calculation whenever possible. Try this checkpoint without copying the example. Why should a system solution be checked in both equations? Decide which mathematical fact controls the answer. Pause and write one line of reasoning before committing. A visible decision is easier to inspect, explain, and correct than an unsupported guess. Focused hint. An ordered pair is a solution only if both original constraints hold. Use the hint to repair the setup, then finish the reasoning yourself. The accepted answer is, it must satisfy both relationships simultaneously. Explain why it works, and name the earliest line that would reveal a likely error. The central message is to preserve equality through each operation. Combine that with a discipline to choose elimination or substitution. Finish by remembering to verify a system in both equations. A result becomes dependable only when the method and verification are both clear. Reflection. Did the chosen method reduce work or merely follow habit? Name the exact point where an incorrect path would first become visible. Practice one fresh problem for 8 to 12 focused minutes. Keep the work readable, verify independently, and carry the routine into the next session. Before moving on, close the notes and explain the method aloud from memory. Then invent one small variation, predict how the answer should change, and verify that prediction with a complete calculation.